Great. Thank you very much for inviting me. And I'm also really happy to be here for the year. Okay, so first I wanna write down maybe the classical reaction-diffusion equation, namely the Fisher-KPP equation. Okay. So KPP stands for Kolmogorov, Petrovsky, and Piskunov. And this PD was written down and studied in the 1930s first. So I'm going to have some positive number, theta bar. My PD is as follows. So it's a diffusion equation with theta bar being the diffusion coefficient. And it has this reaction term. Okay? So m is a function of x. So say an r, and then t in 0 infinity. Has some initial data. Some positive and non-negative initial data. So what does this equation represent? So some sort of something that's diffusing, but whose growth is limited by its environment. That's what this 1 minus m term means, right? Because I think when Fisher wrote this down, he was thinking of genes in a population. You can also think of, and the context that we'll think of is ecology. So m is some density of individuals. When there are too many of them, they stop growing or grow more slowly. So we'll talk about, in the PDs, and we'll talk about what we're interested in as let's see, the first two words in the title is front propagation. So what do we mean by a front? So notice here, this is a uniformly parabolic equation. This is a positive guy. So the solution, so we usually start with this guy compactly supported, but the solution immediately becomes positive everywhere. So we want, so throughout today we'll see slightly different notions of what it means for the solution to propagate. So first I'll write down one of them. So I'll write down, so when this equation was introduced, independently by these by the KPP folks and by Fisher independently, both in 1937, they showed that suppose, let's say M0 has compact support. So they showed that the population, or I'll always say population, spreads at a linear rate. So when I write down the front, we'll see that the front, and moreover, they characterize the speed. And that speed is 2 times radical theta bar. So the way that, one way to say this is, so for any speed less than this, or for any number less than this, if I look at the region in front of sort of behind the front, then there, so maybe I'll write it down. Maybe I draw a picture. Okay, and then sort of where the second one represents where the individuals haven't reached. So let's say, let's draw a picture. So I'm going to draw a picture of of xt for, let's say, t large, because this is an asymptotic result as t gets large. So, and this is, for for C bigger than 2 radical theta bar. So if this is the point that's 2 radical theta bar t, then what this is saying is that in this region behind where the individuals are, u is really, really getting near 1. And then past this, u is getting really, really near 0. And I guess something is happening over here. Okay? So u is near 1. Here u is near 0. So another way to track the front is to say I fix a level set of u and to track that. And we'll maybe refer to that notion later in the talk. So this, but the thing to notice is that the location is given in terms of t. It's not a power of t. And in fact, this is seen in many invasive species. So there have been somehow natural experiments where an animal escapes from some sort of farm, and they track how it spreads, and they find that it really does spread linearly. So, and mathematically, there has been a lot of study of reaction-diffusion equations, as well as even of this equation, so finer propagation, finer results on the asymptotics, or with maybe different types of reaction terms. So what we're gonna focus on today is a reaction-diffusion equation where the reaction term is non-local. So I'll write down, and it comes from a ecological motivation. So I'll write it down, and I'll tell you the motivation. And I spoke on this topic in that short talk, so maybe I won't dwell. And there, I think I had lots of fun explaining the ecology, and I guess I'll do so today, but maybe I won't, not as much as then. So
is there a natural profile that emerges in this
yes. So you can. So there exist traveling wave solutions to this guy, and it turns out that solutions actually converge to this shape as time goes on. Yeah.
That's what you've written there, basically.
Yeah. I haven't. Yeah, pretty much. But it's weaker than what I've just said aloud. So what I've written is weaker than what I've said aloud. Okay. So I'll write down the PD that we'll study today, and then I'll comment on it. So here, I have a function of 3 variables, so x and r. Theta, so before I had it a parameter, now it's a variable. It's one of the things my function depends on. So theta, and that it will be a trait that individuals possess. So maybe I'll do that later. And time. So this models a species that was found in Australia, and it was seen to have spread more and more every year. So the propagation of the front was accelerating. And it was also noticed that the individuals in the new territory, so a newer generation, could run further and faster. And it was posited by ecologists that there was evolution in the sort of running ability, in motility, and that was driving this acceleration of the front. So this is what the PD models. So theta represents the motility of an individual. So bigger motility means you diffuse faster in space. This diffusion in this trait models the mutation from generation to generation. And why is there this integral? Well, the reaction term represents the competition of individuals for resources. So somehow all individuals in a given spot compete for the same resources regardless of their length of legs. So that's why you want to consider and this integral term. Okay?
So theta runs over
Right. So in fact, we'll see that there's different behavior depending on what this big capital theta is. So one of the cases is when it's just an interval, so like 1, 5. And the other is when it's the positive real line but bounded away from 0. Okay, and 5, I just don't want to have extra notation. This can be any number, and this 1 can be any number that's bigger than 0. So in everything I say today. Okay, and of course, everything, any constants that appear will depend on what this number is, and in that situation, what that number is. Okay, and this guy has Neumann boundary conditions on the boundary of this trait space, and again has positive initial data. Okay. So this was introduced in 2012, and so what we'll see today is that in this situation, when this trait space is just a finite interval, you have a constant rate of spread, or a linear rate of spreading, like in the KPP case. On the other hand, in this situation where the trait space is 1, it goes all the way to infinity, there you see acceleration. Okay? So what I want to do, so the outline of the talk is, first I will maybe give a very vague sketch of a proof of what's happening in the KPP case. Then I will talk about what happens in the first case, and then in this unbounded trait space case. So before I begin, maybe I'll point out a important difficulty, and we'll see it's not just a difficulty, it's essential to the character of the problem, the fact that this guy is non-local. So this equation doesn't have, so I call it, so it's CT for cane toad's equation. That's the creature that was invading Australia. So this guy doesn't have comparison principle. You don't right away see that solutions are bounded. And in fact, okay, so and you don't have comparison principle. So a lot of the techniques that you might want to use are not available to you. Okay, so maybe part 1 is propagation for KPP. So in the proof in the 1937 works, the way that they go is, in fact, first a traveling wave solution is constructed, and then comparison principle is used to trap your initial data under the solution, and that gives you the upper bound on the rate of spreading. Now that certainly is not going to work here because there's no comparison principle. Okay, so I want to show how to find how to study propagation in KPP using a different approach, and one that doesn't use comparison principle, so it'll be more handy for this situation. So this will be via a connection to Hamilton-Jacobi equations. So this is due to Friedland in, let's say, 85. So what I will present was done by Friedland using probabilistic methods, and Evans and Tsouganides in 89. And then, yeah, okay. Great. Using PDE methods. So let's consider the following. So a rescaled version of this guy. Okay. So this arises under the rescaling. Xt goes to x over epsilon, t over epsilon. Okay, and the goal is to study, so looking at large x's and large t's is the same as looking at small epsilons. So in the original problem, in the original scaling, large space and time is small, corresponds to small epsilon in the new problem. So I'll just a caveat maybe that here to do this, I won't actually do things rigorously, but I don't want to write anything false. So their work applies when all of the m epsilons have the same initial data. So that's not quite, that means that the solution to the KPP equation rescaled is not exactly this m epsilon because something happens to the initial data. So you can either think of it as a related problem, or you can think that actually they are the same, but the initial data there, m0, is invariant under x goes to x over epsilon. So maybe it's like the indicator function of the negative half line, and you're looking really at front, this really, this invasion. So, okay. But I don't want to say more about that. So let me label this guy KPP sub epsilon. So notice that if these m epsilons were to converge to something, let's say nicely, this guy would disappear because there's an epsilon, and this epsilon square would disappear. So you'd have 0 equals to m times 1 minus m. So I would have then in the limit, this m is either 0 or 1, okay? Which is, okay, we saw that that's the case there. And the goal is now to determine what are the regions where m is 0 and what are the regions where this limiting guy is 1. So you can perform the following transformation. It's called, so you define u epsilon via this exponential change of variables. Okay, so since your m is positive, defining this u epsilon makes sense. Moreover, by the comparison principle, so let's also say our initial data is between 0 and 1. You get that your solution m is between 0 and 1, or certainly it's bounded no matter, yeah. So because the m epsilons are bounded, that means that the u epsilons have to stay, or okay, so right, the u epsilons cannot be going to something negative, right? Because if they went to something negative, this guy will blow up. So let me write down what I just said. So, well, first, you can write down a PDE for what this u epsilon solves. So it'll be u epsilon t plus theta bar u epsilon x squared is equal to, so let's say plus epsilon u epsilon x is equal to 1 minus m epsilon. Okay. Oh, sorry. Okay. So, and what I just said aloud was, so say u epsilon converge some u bar. So you know that u bar is non-zero. Okay, and moreover, just from the definition, we see that the regions where, so the region where u bar is positive, that'll correspond to the limit of the m epsilons being 0. And similarly, the region where u bar is 0, that'll correspond to the limit of the m epsilons being 1. Okay? So determining this limiting u bar is equivalent to understanding the propagation in the original problem. Or rather, determining the 0 set of this u bar is the same as determining the propagation in the original problem. Okay, so I want to find u bar. So how do I do this? Well, or what might this u bar be? Well, in fact, we can determine what PDE this u bar will solve. Okay, so if I look at this epsilon PDE and I want to take this limit epsilon goes to 0, so I certainly know this, and again, in reality, you actually can do this, and this guy does disappear, okay, as you'd expect. But what happens to this m epsilon, right? So I'll write down, so you can, I'll write down what you can see pretty easily, but I won't. Turns out u bar solves the following. So there's the equation you would expect. But it's the minimum of this guy and u bar itself. And you get that this is 0, then with some initial data. So the proof takes maybe 2 minutes, but I don't want to use those 2 minutes for this. Great. So in this situation, it turns out, okay, in fact, this guy, you can characterize this as the maximum. So this is something quite special, where U-twiddle solves just the naive PDE. Okay. So I'm saying that this U bar that characterizes our problem solves this kind of funny looking PDE, but it's actually the maximum of 0 and this function that solves a more usual Hamilton-Jacobi equation. Okay? And this is kind of a special property. And so what does this equation correspond to? Notice that if I had started, let's look at KPP epsilon. If I started by looking at this guy linearized around the 0 solution, so that corresponds to just having that term there. Okay, so if I had started out with this not being there, okay, so now not here, okay, then when I went to write this guy down, I would just have that this term is not here, okay? And then in the epsilon limit, it would be exactly what you expect it to be, this U-twiddle. So one conclusion is that in this setting, the linearized problem determines the propagation in the nonlinear problem, okay? So this corresponds to the linear problem. So this corresponds to linearized KPP. And it determines the propagation in the main equation, and that's not always the case. But okay, so I promised that I would tell you how to conclude this result, and
But this is basically burgers, is it?
no, it's not burgers, because this has this. It's the square of. It's not u
Yes.
times it's
No, I
right.
see, but if I took a derivative, I would get burgers.
Yeah. Yes.
So it would be the derivative. If I took a derivative,
Oh, and
I
this-
would get burgers.
Yeah, this is like the best Hamilton-Jacobi
This is
equation,
Hamilton-Jacobi, yeah.
because this is a quadratic,
Yeah, yeah.
so it is the convex function, I guess.
Yeah.
Well, anyway,
So this is the Hamilton-Jacobi.
yes, this is the Hamilton-Jacobi equation. So this.
What I don't understand is when you took the
Oh,
epsilon
why does this? Where does this come from?
zero- No, I guess I probably understand why, but I don't understand how you erase the epsilon. Okay, and then you had the 1 minus 1 plus m. So what did you do with that?
Oh, okay. So I should then probably say why u bar solves this. Why the limit of this equation without the orange stuff solves this.
That I sort of.
Oh, okay. Okay.
Because that's a little bit like So there's variational techniques for solving things in one.
I mean, and to see that it solves this, you just, well, maybe I could tell you later.
Okay.
But it's very easy. You just say, and anyway, I could tell you later.
But you've ignored this one. Minus
Oh,
1 plus
what
m.
I'm saying is that if I ignore this m,
Then you get
I get that equation.
Okay.
Okay? So maybe I put
All right.
my orange too far.
All right. Fine.
Okay.
Yeah.
Okay. Well, great. So I want to say that because this is quite a simple equation, you can find its zero set. So I'm not going to do that. So, or you find that it's positive set, and you have to keep track of the initial data. So with correct initial data is the set of xt such that this guy is exactly what you expect. Okay? Great. So let me so notice that what I didn't use is I didn't use any comparison principle, and what I did use is I used that this m epsilon was uniformly bounded. Okay? So
I didn't quite understand. So how do I see this? Okay, I follow that equation.
So-
How do I get that immediately from that?
it's not immediate, but you can compute. If you keep track of the initial data correctly, you can then compute the solution to this, and you can find that this holds. Okay. So so I really should move on. So hopefully, so let me do this. So the reason that I did this is I wanted to show why a Hamilton-Jacobi equation might come up when studying reaction-diffusion equations. And I wanted to point out this connection of the linear problem having the same propagation as the nonlinear problem. So this will then have to go quite quickly. So in the case where theta is a bounded interval, so in my work, and now I'm back to the Kane-Todes equation. So I show that in fact solutions to this guy are uniformly bounded. So there exists a constant such that, okay. But this constant, well, in this case, really depends on the number 5. So if the proof really doesn't work for the 0 infinity case. So maybe, because I really like it, I'll tell you the proof idea.
The constant gets bigger and bigger as 5 gets.
Yeah. Yeah. So what's the idea? Okay, so what happens if I want to integrate this Kane-Toad's equation in theta? Okay, so from now on, I'm going to use rho of xt to denote this integral over the whole space. Okay. So if I integrate the first term, I get, in theta, I get rho t. Then the second term, I get minus, I can't really do anything with it. And then the n theta theta disappears because of the Neumann boundary condition. And then I get rho times 1 minus rho. Okay, so I wish I were a calculus student and I could replace, I wish I could replace this term with just theta times integral nxx dx, because that would be theta rho xx, right? And then that would be just the KPP equation for rho. But I mean, this is, oh my goodness, I'm so sorry, d theta, yeah. But yeah, so indeed, because the integral is in theta, I can pull that theta out. But in fact, this idea is not so bad. What you should do instead, because, right, the trouble is that I'm integrating on the whole interval. If I were to be integrating on some small set, those two would be pretty close. So instead, integrate on some small and the point is the error you make is controlled by this nxx, but that's controlled by the supremum of n. But then through doing this, you can, again, control the supremum of n. And it works out. OK, so I'll make this number 1. So I really want to spend, OK. And I also show that there's some constant. So using methods really, really similar to these. So I'm not going to say anything about the methods for the propagation, but I'll just say there is a constant. So it's in 2, and in this case 2 radical 5, such that, and again, I won't even state it precisely, such that front is at c star t at time t. Okay.
So this c star can be determined implicitly somehow.
Yeah, it's related to, if you do this method, some more complicated Hamilton-Jacobi equation pops out, and that's related to that. But the reason that I write down this range is that this corresponds to KPP equation with theta bar being 1, and this corresponds to KPP equation with theta bar being 5. So at least the ecologists will not be freaked out, because having you somehow can't do worse than the shortest legs and better than the longest legs. In fact, you do somewhere in between. And other folks, so Bouen and Calvez, established that actually there exist traveling front solutions to this equation with this speed. But you can't use that result to deduce propagation because there's no comparison principle. So I use this method. Okay, wonderful. So I'm going to spend the rest of the talk.
So is the statement then that if I start with arbitrary positive initial condition, that I will have this front speed?
No, it's of this. It concerns the analogy of this equation.
Okay. So if I mean with KPP, if I start off with, I get this speed of the.
Yeah, for KPP, arbitrary,
Yeah.
any
So
compactly
so
supported.
You get different speeds for different data here, or what?
So I'm not exactly sure what is the best. So for KPP, it's known that if you start with somehow a solution with worse tails, you get different propagation. I don't know of any such results here. In fact, there are more results available past this, but I won't, more finer location of the front, but I won't talk about them now. Okay, so let's, great. So where do I want to write? I'll write over here. So what I'm going to do for the rest of the talk is essentially just describe the different results available in this one infinity situation, and which demonstrate the different phenomena that can happen in this equation. So first of all, okay, so let's write part 3. Okay. So what kind of propagation do I expect? So the ecologists have told me it's not going to be linear. How do I do any? There are a lot of things that are not linear. Okay, so what might I think? So this is maybe the most hand-wavy few sentences. So what to expect in terms of propagation? Well, if I just look at what's happening in the theta variable, I have it's sort of KPP-like, right? There's no diffusion coefficient. So location, and we know that for KPP-like things, the front travels linearly, okay? On the other hand, the location of the front in X, well, that should be like the square root of the diffusion coefficient times t. So radical theta times t. But we said that theta was like t, so this should be t. This is t to the 3/2. Okay? And in fact, this worst hand-wavy guess is actually correct. So we do find, so all the results that I'll show find propagation with rate something times t to the 3/2. Okay? So let's, so notation. So maybe let me circle this. Okay. So here's how I'll keep track of the fronts in this situation. So for a positive number, I'm going to use xm of t to denote the largest x, such that my rho is bigger than m. And I'm going to use the x lower bar of t to denote the smallest, and I should say, I guess, x, I just put both of them positive, such that rho of xt is smaller than m. Okay? So what I'm doing here, so let's say this is my, so the point of doing this is, so as you asked, in the KPP situation, the solution kind of becomes monotone, But here, in the non-local situation, there is no, there is reason to think that it does, but it's only numerical evidence. There's no rigorous results on the solution having any monotonicity in X. So if you want to talk about front, you really have to keep track of these two quantities. So X bar M is the large. So if this is my value M, and this is my rho, this is X, and this is rho of XT. So in this picture, it looks like the first time that my guy hits M is here. And then the last time it hits M is, I guess, over here maybe. Okay. So the first result that I'll state concerns the local version of CT. So namely, where you replace the integral in n by just n itself. And maybe I'll put some twiddles on here. Okay, so this is CT. Okay. So this was a theorem of Bouen, Henderson, and Rizhik in 2017.
So there's something that's bothering me.
Yeah.
Maybe this actually clarifies it. I don't. Are you missing in your equation? Are you missing an n theta theta or something like that?
There it is.
I couldn't see what that was.
Oh, okay.
Okay, thank you.
Yeah.
So there is an n theta theta.
Yeah.
I was very puzzled about that. Okay. So okay, good. So you have a diffusion in both.
Absolutely, yes,
both
absolutely.
the, yeah.
I'll be sure to write more clearly next time.
I thought it was n infinity. I thought you were kind of.
Oh, yes, they do. It does look like infinity, doesn't it?
I'll correct that in my notes.
Okay. Right, so what these folks show is that for, let's say, for n twiddle, so they look at compactly supported initial data. So then the limit as t goes to infinity of this guy is 4/3. Okay, so for any positive. So what they're saying is that so if I want to draw a picture, then again, this is rho of, or I'm kind of using notation because here I have this n twiddle of x. Oh no, sorry, rho of x t. So I'm not abusing notation. This is literally correct. It's about the integral of their function. So this is this guy for large t. It says that, okay, that somehow if this is m again, then the last time that my guy hits m is located around 4/3 t to the 3/2. And this is x bar m. Okay, so that's pretty nice. You really know where it is in this local case. So now let me state the corresponding result for the full Kane-Toth equation. So So again, let's do. So let n solve cane toads. Then, so they find that lim sup as t goes to infinity of this guy is less than or equal to 4/3, again for any m positive. And moreover, so I should write for any epsilon, there is some number. You can assume it's usually quite small. So in other words, they're able to control, I guess, anything from above, but to control from below, they can only do very small numbers. And moreover, this is not 3/4. Okay? So again, let me draw the picture. What they're saying is that, so let's say this is somehow 4/3 t. And so what this number is like 1.689. Okay, so it's smaller than 4/3. Now I can't add. Okay, I'll just believe what I'm saying. Okay, so what they're saying is that xm is located somewhere over here, but to get a lower bound, they can only put it somewhere in this region. So there is this big gap. Okay? And they conjecture that this is a fault of their proof, and that actually this number should be 4/3, like in the local case. And by the way, let me also mention what is special about this 4/3 is that if it's also the propagation speed in some sense of the linearized problem. So somehow the local problem propagates the same as the linearized problem, and they conjecture that the non-local one does as well. So this is what the last result that I'll state seeks to answer. And the answer is actually no, that the non-local problem does not propagate with speed 4/3 t to the 3/2. It's something else. Okay? So, oops, goodness. So theorem, this is Calvez, Mond, Henderson, Mirahimi, and myself from late last year. So there is an alpha star in this range, and strictly in this range. So I'll write it down, so that this x lower bar is at most as far as t to the 3/2 alpha star. And so for all epsilon, there's a c epsilon such that the lim sup as t goes to infinity of the upper guy is bigger than alpha star times 1 minus epsilon. So this result, so all of these results are much weaker than the ones available for the KPP situation, and weaker than the one for the theta being 1, 5, although I didn't write it down. And in some sense, right, because it has lim sups instead of limits, lim inf instead of limits. And again, this reflects the fact that, so if you knew that your solutions were somehow monotone in the limit, you could deduce stronger results, but you don't know that. So what do I want to comment? Okay, so I want to comment that this shows that the propagation, so maybe I'll go over.
This is for the non-local
Yes.
case, right?
Yes, so this is 4. Okay, to the equation. So maybe, since so let me, okay, maybe I'll just say in words. So this shows that having this non-local reaction term, it's not just something to make our lives more difficult or more interesting. It actually has a real impact on the problem, because again, the propagation in the local case and in the linear case are different than the propagation in the full non-local problem. And notice that this is also interesting because, as we saw in the KPP case, the linear problem determined the propagation in the full problem, but here it's not the case. And I think the term for this is like a pulled front, because the linear problem I keep referring to is linearized at the 0 solution. So it means that the individuals really close to the edge of the front are somehow driving the propagation. Whereas here, this demonstrates that that's not the case. There is other elements to the propagation. Okay, so maybe I wonder if I have time.
Can I ask you about this result up here? This is for the one without the non-local term, right?
Oh no, this is for the full. This is for the
full.
yeah,
Okay.
and this is for the one without the non-local term,
Okay.
with exactly having this. Yeah. Maybe what I will. So I'll just say it in words, or so the strategy of the proof and the differences between the proofs are as follows. So you get your intuition, I guess, by doing this rescaling and looking at this epsilon problem. So what these folks do is they look at the, you know how when we looked at the KPP case and we dropped that m epsilon, we got a simpler Hamilton-Jacobi equation. So that's essentially what we do, what they do, sorry. But what we do instead, we still cannot look at, okay. So what we do instead is somehow replace, so maybe I'll say, so maybe I lied when I said that other thing was the vaguest thing I'd say in the talk. So replace, so look at the problems that you get by replacing a rho by some sort of indicator function of minus infinity alpha t to the 3/2 of x for various mu and alpha. So why would you want to do some, and you use this to find the Hamilton-Jacobi equations, I guess, since this is a family that govern your behavior. So why is this useful? Well, because you can make arguments of the sort, suppose the front is located at some place, let's say alpha t to the 3/2, that means that rho is 0 behind the front and sort of bigger, so rho is 0, I guess, in front of the front and bigger behind the front. And you can refer to the corresponding one of these problems. Okay, but I will stop here. Okay.